Good morning. So far we have seen how to draw Lewis dot structures. It is clear that as I mentioned before, from the Lewis structure you cannot tell or predict the shape of the molecule. How to tell the shape of the molecule? So, if you see some object, you can tell the shape of the molecule. Okay, it is a sphere or rectangular or square, like that. If you see the object, you can tell that, but molecules cannot be seen by our naked eye. Then how to see the shape of the, how to tell the what is the shape it has? Then that can be still one can find out the shape of the molecule by doing experiment, spectroscopic method. Another method is the single crystal X-ray diffraction method. That those things we are not going to see here, but however, one can tell the shape of the molecule using the model called VSEPR model. This is called valence shell electron pair repulsion model. Electron pair repulsion model. So, using this model one can predict the shape of the molecule. So, what is the principle behind this model? You can see that from the title, valence shell electron pair repulsion. So, if you take two electrons, they repel each other because the charge on the two electron is the same. So, when they approach each other, they repel each other, they cannot get closer because they have the same charge. So, electron pair means a pair of electron is involved in forming a bond. So, as a result, when there is a repulsion between a pair of electrons. So, that is why electron pair repulsion. And then which electron pair repulsion? Electron pair repulsion, electron pairs present in valence shell of an atom. So, that is why we are going to tell the shape of the or predict the shape of the molecule based on the electron pair repulsions, repulsions experienced by the electron pairs present in the valence shell. So, that is why this model is called valence shell electron pair repulsion model. So, if you take a region of electron density, I mean here a bonding electron pairs. So, region of electron density means so that is which are equal to bonding electron pairs, and then you have lone pair, lone pairs, you have lone pairs or unshared electrons you have. So, if you take a molecule, it has surrounding, so a center, you have a central atom surrounded by a terminal atoms which are connected to the central atom by bonding. So, each bond is consisting of 2 electrons. In addition, the central atom can have a lone pairs. So, there is a repulsion among them. So, there can be a repulsion between the bonding electron pairs. For example, you take a molecule A and it is surrounded by a molecule B, atom, terminal atom B, another atom B. So, A is a central atom, B is the terminal atoms which are connected to the central atom A by bond. So, this is a bond. So, that a bond means 2 electrons are there. So, here there are 2 electrons are there. Now, the whole molecule, that is A, B2 molecule is stable compared to its atoms. So, the atom A likes to have both atoms B bonded to the atom A. So, but the problem is there is a repulsion between atoms B. So, they do not like each other, like that, they do not like each other, but the central atom like to have them together. So, the best way that the central atom can have these 2 B atoms which are repelling each other is to have them as far away as possible. Okay. Okay. The central atom A like to have B atoms as far away as possible. Okay. They have to be as far away as possible. Why? Otherwise, there is a repulsion between them. So, if B atom reduces electron density, electron repulsion between atoms B by keeping the B atoms away from each other. Okay. In such a way that there is a less repulsion, a minimum repulsion between them. So, the best way to arrange two atom, that is B around A, is in a linear fashion. So, if you take a circle, in the middle you have atom A. Okay. In the circle is a 360 degree. Okay. So, if you divide the 360 degree, 180 degree will come. So, you can put atom B here. So, the angle is 180 degree. Okay. So, 180 degree, that is the best way of arranging atom B around the central atom A. Okay. Any arrangement less than this, okay, any arrangement having angle less than 180 degree will produce more repulsion. As a result, the structure is not stable. More repulsion means energy is positive. Okay. Repulsion between electrons will lead to a positive energy. So, energy should be negative, that is more stable. So, in this case, if you arrange these two atoms, for example, A here like that, okay, here. So, the angle between two B atom is 90 degree, okay, is 90 degree. Now, because it is 90 degree, they are closer. B atom, both two B atoms are closer to each other. So, the repulsion is more. So, energy is positive, energy is more, which is not favored. But if you put the B atom in this way, okay, the angle is 180 degree, the two B atoms are away from each other. As a result, okay, the repulsion is avoided, energy is minimum. So, that way, okay, you can tell, using based on this concept, you can predict the shape of the molecule. Okay, that is why, okay, the shape of this type of molecule is linear. Okay. For example, carbon dioxide you take, okay, carbon dioxide. Okay. First you have to do a Lewis dot structure for carbon dioxide. Carbon dioxide, so valence electron 4 plus 2 into 6 electrons, okay, because 6 is the valence electron of oxygen. So, you have 12 plus 4, 16 valence electrons are there. Okay. So, 12 plus 4, 16. So, you arrange them. So, C, okay, approximate shape, you can arrange them. So, arrange the two oxygen atom around the carbon atom. So, you can then you have to spend 4 electrons to form 2 bonds. So, 4 electrons are gone, minus 4. So, remaining is the 12 electron, arrange them such that octet is reached for every atom. So, 12 electrons are there. But if you look at the central carbon atom, it is not achieved 8 electrons. So, you have to convert this lone pair into a bonding pair. This also you convert, and then you can have C double bond O like that. Okay. Now, octet structure, so the octet of electron is achieved by the central atom, because 2 electron, 2 electron, 2 electron, 2 electrons, there are 8 electrons, here also 8 electrons, here also 8 electrons. So, the octet structure is over. The same structure you can also write, for carbon dioxide, you can also write in this way. Both structures, both are correct, okay, both. So, I mean this structure you can write this way also, and you can also write this way also. Okay. Both structures are correct as far as Lewis dot structure is concerned. But what is the shape? As you can see here, in this structure, two atoms are occupying positions which are having 180 degree. They are far away from each other. But in this case, okay, the angle between two oxygen atom is 90 degree. So, because this is one region of electron density, this is one region of electron density. Okay, electrons are repel each other, they do not like to be closer to each other, they like to be as far away from each other as possible. So, as a result, the correct structure for carbon dioxide is a linear structure. Although it has a double bond between the carbon and oxygen, it should be taken as one electron region. So, it has okay, 2 bonding pairs, but connected to the one oxygen atom. So, this is a 1 electron region. Okay. So, this is 1 electron region, although it is connected to a carbon atom by double bond, but it should be taken as 1 electron region only. Okay. So, as a result the shape of the molecule is linear. For carbon dioxide, structure of the cell is linear, which is what observed experimentally. So, the model predicted, that is a VSEPR theory model predicted the shape of the carbon dioxide correctly, okay, which is consistent with the shape determined by experimentally. Now, so if you take a, okay, now let us go to another case. You take a molecule of this type, a central atom BF3 boron trifluoride. Here central atoms the boron, the terminal atoms are fluoride. Boron is surrounded by 3 fluorine atoms. Okay. Now, first job is to draw the Lewis dot structure. Boron valence electron is 3. Okay. So, fluorine, okay, 3 into 7 electrons are there for fluorine, each fluorine atom 7. So, it is a 21 plus okay, 24 electrons, 24 valence electrons are there. So, if you arrange that B, okay, so there are B is the central atom because it has the highest bonding capacity, okay, because it has 3 unpaired electrons. So, you can arrange, okay, 3 fluorine atom around the boron fluorine atom, so around the boron atom, okay, there are okay, 3 bonds. So, each bond is 2 electrons, so 6 electrons are gone. So, here is remaining is the 18 electrons. 18 electrons should be distributed in such a way that each atom has 8 electrons. You can distribute this way. Okay. So, 18 electrons are consumed, but here you can see here the central atom does not achieve the octet rule. So, then actually what you can do is you can pull this lone pair to here and then you can have that 8 electron around that. So, as of now the number of electron around the boron atom is less than 8 electrons. So, this is called electron deficient or Lewis acid. Okay. This is electron deficient, okay, or Lewis acid. So, BF3 is a Lewis acid molecule, Lewis acid. Now, those concepts you will be studying later on. Now, the point here, here we are concerned about the shape of the molecule. Now, okay, now this molecule contains how many pairs of electrons, how many regions of electrons. This is one region of electron. So, this is a Lewis dot structure. So, one has to write the Lewis dot structure first. Okay. Next step is to find the shape of the molecule based on the electron pairs. That electron pairs can be bonding electron pairs or lone pair of electrons. So, using okay, those pairs of electrons, you have to draw the shape, approximate shape. Then we have to think about the repulsion between the bonding okay, repulsion between the lone pair repulsion, lone pair bonding pair repulsion, and then bonding pair repulsions. Okay. So, this here in this central atom, there are 3 bonding pairs are there. So, when there is a 3 bonding, 3 atoms are connected, 3 regions, this is one region, this is another region, there are 3 another regions. So, if you take a circle, okay, this is a boron atom. Okay. So, the circle is a 360 degree, should be divided by 3, then you will have 120 degree. So, that is a okay. So, the angle between here is 120. Okay. So, 120. So, that is the best way. So, you have what is the why 120? Because at 120 degree you can have these 3 fluorine atoms far away from each other. So, if suppose if you draw any other structure B, for example, like this, okay. So, like this, okay, you can draw as far as you can put the electron here. Okay. So, here still the Lewis structure is correct, but the angle between them is 90 degree. So, it is not a okay, 90 degree. So, this electron density is repelled by this electron density. So, they repel each other, repulsion is more because the angle between them is lower. But if you look at arrange the 3 atom in this fashion, okay, 120 degree away from each other, okay, then the repulsion is reduced. That is the purpose. You should have a arrangement where there is a minimum repulsion between the electron regions. Okay. Electron regions means bonding electron pairs or lone pair of electrons. So, that angle is increased compared to this one. So, when the angle is higher, less repulsion. Okay. So, this is the best arrangement for BF3. then the shape, what is the shape? When you have a central atom connected to a 3 atoms, then the shape of this molecule is okay, trigonal planar structure. It is called a trigonal planar. This is called a trigonal planar. Okay. So, it is all in a plane. 3 fluorine atoms are in a plane. So, trigonal, okay, trigonal planar structure is the correct shape of this molecule. Now, let us see another molecule, for example, CH4. So, as you know that so methane, you can draw a Lewis dot structure, and then you will see that arrangement of 4 hydrogen atom around the central carbon atom in this way. Okay. Then you can see that, so how many pairs of electrons are there? It contains okay, 4 electron pairs. So, you have a central atom surrounded by 4 electron pairs. Okay. Now, okay, so as I mentioned before, if you take a circle, okay, in middle you have a carbon atom and arrange them, okay, divide this 360 by 4, then you will have 90. Okay, 90. Now, if you put hydrogen here and here, okay, it is a kind of square planar geometry, but the angle between them is 90 degree. But this is not the correct structure. Square planar is not the shape of the methane. Okay. This square planar will come if you arrange the 4 hydrogen in a plane like that. But if you arrange the 4 hydrogen atom in this fashion, that is the central carbon atom. Okay. So, you put 2 hydrogen atom on a plane and one of the hydrogen atom, okay, towards you, this is towards you, and one of the hydrogen atom away from you. Okay. Then you will have the angle between them is 109.5 degree. So, compared to this structure is a square planar geometry, square planar shape, okay, shape and geometries are interchangeably used here. And then here 90 degree between the 2 electron, this is 1 electron density, this is another electron density, the angle between them 90 degree. Here for the same atom, for the same electron regions, okay, the angle is increased. How much is 109.5 degree. So, the angle is higher, the angle, the less the repulsion between the atoms. So, this structure is favorable structure for methane, and the shape of this, name of the shape of this molecule is tetrahedral. Okay. Name of the shape of this molecule is tetrahedral. I can explain that using a model system. Okay. So, this is a shape of the tetrahedral, as you can see here, this is a shape. So, if you look in this way, okay, if you look in this way, this is hydrogen, consider this is a carbon atom, middle carbon atom, and these and these are hydrogen atom, which are bonded. So, this is a bond, this is are the 4 bonds are the 4. Now, okay, so you can see here in this way, this hydrogen is away from you. So, which is given in this way. Okay. This hydrogen is towards you, which is given in this way, okay, solid line, and these two, okay, and this atoms are in a plane. Okay. So, then if you look at the angle between them from here to here, and you can see that which is 109.5 degree. So, okay, so that is why, so basically, okay, so you have arranged molecule in a tetrahedral fashion. Okay. So, in a tetrahedral fashion. So, the angle between the 2 hydrogen atom is 109.5. Okay. So, that is the best arrangement of arranging 4 regions of electrons around the central carbon atom compared to this one. This one, the angle is 90 degree, more repulsion. Here angle is 109.5, so repulsion is less, and the structure shape of the molecule is tetrahedral. Now, let us see, okay, molecule of this type. Ammonia. As you know, first you have to write the Lewis dot structure. It has a 5 plus 3 Okay, 5 is a valence electron of 5, is 3 plus 8 electrons. So, you can draw the shape of the you can draw approximate shape of the ammonia molecule. 3 hydrogen atom around the central nitrogen atom. Okay, 6 electrons are there for forming a bond. One more electron, 2 more electrons is there. So, that 2 more electrons should be added to the central nitrogen atom. Now, octet structure is attained by the central nitrogen atom. Okay, for hydrogen it is only 2 electrons. So, this is a correct Lewis structure. Now, how many pairs of electrons are there? It has 3 bonding pairs and 1 lone pair. So, in total 4 electron pairs or 4 regions of electron density. Okay. So, how to arrange the 4 regions of electron density? As we have seen, for this type of 4 pairs of electrons, best arrangement is a tetrahedral. Okay, that we just now we saw that. Then, if you put the tetrahedral, okay, the shape of the molecule, okay, so it has a pair. You can draw like that also. Okay, a pair, a lone pair is shown in this way. This is orbital containing a lone pair of electrons. Now, okay, so what is the shape? Then what is the shape of this molecule? Now, once again, which can be explained in this way. So, this is a nitrogen. Okay, these 3 are hydrogen and this is a lone pair. Consider this as a lone pair and this and this and this are hydrogen atoms. Let us continue, and then so you have a ammonia molecule. Okay, so here is the ammonia molecule. This is a nitrogen atom and these 3 are the hydrogen atom and this is a lone pair. Consider this is a lone pair. So, if you draw a line from here to here and here and here, there is a one face. Similarly, here and here and here, okay, here and here and here one face. Similarly, here and here one face. So, it forms a planar trigonal planar trigonal shape, a triangular shape, forming a triangular. Now, the shape of the molecule is now this is a lone pair of electrons. To tell the shape of the molecule, we should not include the position occupied by the lone pair of electrons. So, this should be removed. To tell the shape of the molecule, okay, we should not consider the position occupied by the lone pair of electrons. Now, you can see that this is ammonia molecule. Okay. So, this ammonia molecule shape of this ammonia, the shape of this type of arrangement is called trigonal pyramidal shape. So, it has a trigonal pyramidal. So, the shape of the ammonia molecule is a trigonal pyramidal because the shape is like this. Okay. So, you should not tell the shape of the ammonia molecule as tetrahedral. Tetrahedral geometry will come if there is a atom in this place. Okay. Like methane, you have 4 hydrogen atoms. So, its shape is it's tetrahedral. But to tell the shape of the molecule, one should not include the region occupied by the lone pairs. Okay. So, you have to tell the shape of the molecule based on only the atom positions. So, for ammonia, the shape is trigonal pyramidal. Okay. So, it is a trigonal pyramidal. So, this is a one face, here is another face, here is another face. So, that is a trigonal pyramidal shape. Now, okay, so now this is then what is the angle between the 2 hydrogen atoms? The angle was found to be 107 degree. So, okay, as far as 4 regions are concerned, the best way to arrange the 4 regions of electron density is by tetrahedral. But it is found that the angle is 107. It is less than 107 is less than 109.5 degree, which is for tetrahedral. Okay, tetrahedral. which is for tetrahedral. So, the angle is 107. What is the reason? So, there is a reason how to explain that lower angle observed here. Now, you have to consider what is the difference between the between a bonding electron pair and lone pair of electrons. So, if you take a central carbon atom, for example, CH4, okay, so you have a bonding pairs. There are four bonding pairs here. So, they are all equivalent. If you take ammonia, okay, you have a 3 bonding pairs and then there is a 1 lone pair. This is a lone pair. So, these are the 4 here, 3 bonding pairs, 1 lone pair. Now, you can see that the volume, what is the difference between the volumes occupied by the lone pair of electron and the bonding electron pairs. The volume occupied by the lone pair of electron is larger compared to the volume occupied by the bonding electron pairs. Why is that? That can be explained qualitatively. If you consider carbon and hydrogen, okay, there is a bonding electrons, which so this bonding electron is connected to two nuclei. Here is the one nucleus, here is another nucleus. So, this is the bonding electron is stretched between two nucleus, okay, two nuclei. As a result, it became thin. Okay, it's a thin. So, it's like that. It is like that. Okay, but if you take a lone pair, it has a link to this atom. This is atom, central atom. This is central atom. Here is a central atom. Okay, the lone pair is connected to its own nucleus only, but there is no atom in the opposite direction. Here there is no atom. So, as a result, this lone pair of electron is not pulled away or not shared. Okay, that is why it is unshared lone pair. Okay, it is not attracted by the nucleus which could be present opposite to this nucleus. So, it is not, there is no two nucleus present for the lone pair of electrons. So, as a result, lone pair of electron has a has free volume. So, it is free to move everywhere. It is spread by itself. Okay, it also itself in such a way that it occupies more space compared to a bonding electron pairs. Okay. If there is a nucleus here, then this lone pair also will get stretched like bonding electron pairs. Since there is no atom nucleus present here, nucleus attract the electrons. So, there is no nucleus here. So, this bonding lone pair of electron occupies more space compared to the bonding electron pairs. Okay. As a result, okay, there is a, because it occupies more space, okay, there is a repulsion. Okay, it pushes the bonding electrons, these are the bonding electron, pushes the bonding electrons down. Okay. So, as a result, the angle is less. That is the reason ammonia has, okay, ammonia angle is, okay, the angle is 107. Okay. If you take a carbon, the tetrahedral, okay, the angle is 9.5. Okay, 9.5. So, here all are bonding electron pairs. Here you have, okay, 3 bonding electron, 1 lone pair. So, since the lone pair occupies more space, okay, as a result, more repulsion. Okay. So, the repulsion can be arranged in this way. Lone pair repulsion is greater compared to lone pair okay, bonding pair. Okay, and then which is greater compared to bonding pair pair. So, the repulsion is highest for lone pair. If there is a 2 lone pairs attached to central atom, the repulsion between them is greatest. So, lone pair okay, repulsion is greatest one compared to, okay, the lone pair bonding electron, okay, bonding pairs, which is less compared to this one. Okay. This is still higher compared to the bonding electron, bonding electron pairs, bonding electron pair repulsion. So the the repulsion decreases from left to right side, decreases. This has lone pair repulsion is the greatest repulsion. So in that way you have a repulsion between the lone pair of electron and the bonding electron pairs, there is a repulsion. Okay. So that is greatest, okay, compared to a bonding electron pairs. So this is a bonding electron pair, this is a bonding electron, there is a repulsion. However, the repulsion between lone pair and the bonding electron is the greatest. As a result, it pushes these bonding electrons down. As a result, the angle between the two hydrogen atom is 107. It is not 109.5, which is typical for tetrahedral arrangement of 4 atoms around a central atom. Here, although you have ammonia, you have a 4 electron pairs, the angle is 107, because the lone pair present on the nitrogen atom pushes the bonding electron pairs down. Okay. Accuses the bonding 3 hydrogen atom closer to each other. As a result, 107 is the angle between the two hydrogen atom, and the shape is a trigonal pyramidal. I hope this is clear. So there is a difference, okay, between the volume occupied by the bonding electron pairs and lone pair of electrons. As a result, using which one can predict the shape and one can explain the difference in angle between typically expected value and the observed value. Now let us see a molecule of water. Okay. So you know that central atom is oxygen atom, and there is a, okay, 2 hydrogen atom attached to this one, and there is a lone pair. There are 2 lone pairs on the oxygen atom. Okay. So the lone pair repulsion is the greatest, as I mentioned here. So because of that, there are 2 lone pairs lying on the oxygen atom. So in total, how many number of electron pairs? There are 4 number of electron pairs. Okay, 1 pair, 2 pairs, 3rd pair, 4th pair. There are 4 pairs. The best way to arrange 4 pairs of electron is a tetrahedral. So including the what is the shape of the oxygen molecule? The shape of the oxygen molecule is not a tetrahedral. It is a bent structure, angular structure. Okay, a bend or angular. Shape of the molecule is angular shape. Okay. So it is angular. So then it is found that the angle between the 2 hydrogen atom is 104.5. Angle is, okay, it is 10 between 104.5 degree. The angle is less. So this is still, okay, lower compared to the tetrahedral angle or the angle found in ammonia. It is 107 only. Okay, it is 107 because it has 1 lone pair, but in water there are 2 lone pairs. So the lone pair repulsion is the greatest. Okay. So as a result, it pushes both lone pairs, pushes the bonding electron pairs come closer. So as a result, the angle is 104.5 degree. Okay. So this, okay, one has to understood properly why the angle is 104.5. Okay, compared to ammonia. So there is a relationship between these 2 molecules, ammonia and water. The number of lone pairs or number of regions of electron is the same. Here 4, here is 4. Okay, when you have a 4 pairs of electron, the usual arrangement is the tetrahedral. So arrange the molecule and then look into the repulsion between the lone pairs and lone pair bonding electron pairs. So here there is a lone pair interactions repulsion as well as lone pair bonding electron pair repulsion. So as a result, the angle is lower in water compared to ammonia. So from these considerations, we can tell, okay, we can predict from these repulsions, we can predict. So if you can, I can tabulate them, number of electron regions, if we consider, and the arrangement. Okay. If you have number of electron regions is 2, the shape is linear. Okay, shape is linear. If you have 3 regions of electrons, the shape is trigonal planar. If you have regions of 4 regions of electron density, then shape is tetrahedral. If you have 5, the shape is trigonal bipyramidal. What is that? We will see that little later on. Then if you have 6 regions of electron density, the shape is octahedral. So one has to keep in mind these type of, if you have 2 regions of electron density around a central atom, the shape of the molecule is, or geometry of the molecule is linear. If you have 3 regions of electron density, the shape is a trigonal planar. If you have a 4 regions of electron density, it is a tetrahedral. If you have 5 trigonal bipyramidal, there is another shape possible, square pyramidal. Square pyramidal. So that is like this, that we will see later on. So there is a 2 ways of arranging 5 electron regions around the central atom. That one is a trigonal bipyramidal, another one is square pyramidal. So suppose you have, let us see 5 regions of electron density. So this is called trigonal bipyramidal. So this is called a trigonal bipyramidal, that can be drawn in this way. You have a central atom. For example, let me take a molecule PF 5. Central atom is the phosphorus, and then 5 fluorine atom can be drawn in this way. This way. So the central phosphorus atom contains 10 valence electrons, that means 5 pairs of electrons or 5 regions of electron density, which can be arranged in this way. The shape of, then the shape of the molecule, this molecule is a trigonal bipyramidal. This is a trigonal bipyramidal shape. So in the trigonal bipyramidal shape, these 3 atoms, so 1, 2, 3 are in a plane, because they are all in a plane, and these 2, so then these 3 are called equatorial plane. So these 3 atoms are called equatorial plane. So you can see that, you can draw like that, equatorial plane, and then these 2 atoms are axial atoms, because these are occupying the axial positions. So these are, there are 2 types of arrangement. One is in a planar, 3 atoms are in a planar arrangement, another 2 atoms are in the axial positions. So this way the angle between the 2 atoms, suppose if you take here and here, the angle between them is 120 degree. So this is a 120 degree. If you take angle between this atom and this atom, it is so it is 90 degree. 90 degree. There are 2 types of angle. So this is the best way of arranging 5 regions of electron density around the central atom. Any other arrangement, if you do, that will have more repulsions. As a result, energy will be more. So in addition, there is another way of arranging 5 regions of electron density in this way. In this way, you can also arrange that square pyramidal shape. Square pyramidal shape. So in like that. So these 4 fluorine atoms are in a plane, and then at this top, that is axial position, you have only 1 fluorine atom. So this way also you can arrange. This way also you can arrange, but compared to, so then the question is, which is the correct structure arrangement. So, energetically, if you look at the energy value of these two arrangement, this is slightly lower compared to this one. So, most of the compounds, most of the 5 coordinated compounds except coordination compounds, okay, have this type of this trigonal bipyramidal geometry only. Trigonal bipyramidal geometry is a favorable geometry for 5 coordinated compounds, okay, compared to this geometry, square pyramidal geometry, because energy of this arrangement is slightly higher, okay, compared to this one. So, however, there are several molecules are known having this type of geometry, but most of them having this only. So, that is a way of arranging 5 atoms around a central atom, if you have 5 regions of electron density. Similarly, what about 6? If you have 6 regions of electron density, then the best way to arrange them is by octahedral manner. What is octahedral shape? Okay. This is octahedral shape. This is the octahedral shape. You can see here this is central atom connected to a 6 atoms. So, you can see that 1, 2, 3, 4, 5, 6. There are 6 atoms connected to the central atom. So, this is a shape of octahedral. Okay. That is the best way of arranging 6 regions of our electron density around a central atom of this. Okay. Any other arrangement, okay, will lead to a higher energy state, which is not favorable. So, more repulsion will be there. So, this is the best way to arrange 6 regions of electron density around a central atom. And here, okay, so these 4 atoms, okay, these 4 atoms are in a plane. These 2 are in the axial positions. Now, let us see few more molecules. Okay. So, let us see this type of molecule, sulfur tetrafluoride. Now, first job is to draw the Lewis dot structure. Sulfur has 6 electrons. Okay. So, it is because it is in the oxygen group 6 plus 4 into 7, 7 is a valence electron of fluoride. So, okay. So, in total you have 32 electrons. How much? Okay. Sorry, 34 electrons. In total you have 34 electrons, 34 valence electrons are there. So, you can draw the approximate geometry. Okay. You can arrange the sulfur is a central atom, and then you can draw, okay, 4 fluorines around the central sulfur atom. So, there are 4 bonds are drawn. So, 8 electrons are gone there, 8. Okay. So, the remaining is 26 electrons. Okay. So, 26 electron can be arranged in this way. Okay. 6 plus 6 plus 18 plus 6. Okay. So, 24 electrons are gone. So, minus 24 electron, remaining is 2 electrons. So, that 2 electrons should be added to the central atom. So, the remaining leftover electrons should be added after filling the octet of terminal atoms. The remaining leftover electrons should be given to the central atom. Now, you can say, so this is the correct Lewis dot structure. Okay, it's although central atom does not obey the octet rule. Okay, so it's exceeding the number of more number of electrons. Okay, so however, we arrange the electron around these atoms using the, whatever valence electrons are available. Now, you can see that. So, how many pairs of electrons? Now to tell the shape of the molecule, you have to look at the number of pairs of electron or number of regions of electron. So, 1, 2, 3, 4. There are 4 bonding pairs, and there is one lone pairs. One lone pair. In total, there are 5 regions electron density. 5 region. So, if you if you have a 5 region of electron density, the best arrangement is the trigonal bipyramidal. Okay. So, you can draw the trigonal bipyramidal geometry of this type. So, if you consider these two fluorine atom as the axial positions and these two in the equatorial, and then put the lone pair in the equatorial positions. Now, that I can explain by looking at this model. Okay. So, this is a trigonal bipyramidal arrangement, because you have 5 regions of electron density around the central atom, around the central sulfur atom. So, this is a sulfur atom, okay, and then there are 4 fluorine atoms. Let us arrange them and 1 lone pair of electrons. Okay. So, there are 2 ways you can arrange that. Okay. So, the lone pair, this lone pair can be put in the equatorial plane. So, this is equatorial. So, if you consider this a fluorine, fluorine, and this is fluorine, this is fluorine. So, 4 fluorines are there. Then 1 lone pair you can put in the equatorial plane. So, this is equatorial, because this is equatorial plane. Okay. Trigonal bipyramidal, this is equatorial plane. So, 2 fluorines, 2 fluorines. The remaining one, the last, this position is occupied by the lone pairs. So, you can put the lone pair in the equatorial position. So, there is another way you can arrange that, is to put the lone pair in the in this axial position. So, that you can draw structure like this, sulfur. Okay. So, you can draw like this. So, it is a lone pair, okay, fluorine, fluorine, and fluorine, and fluorine. Okay, you can draw. So, there are 2 ways you can arrange the lone pair in this structure. Okay. The lone pair is, okay, this is a lone pair. So, here lone pair. Okay. So, lone pair. So, the lone pair is in the equatorial position. In this structure, the lone pair is in the axial position. So, here the axial positions. So, between these are 2 ways you can arrange now. So, between these 2 structure, what is the actual structure, or what is the shape of the molecule? Now, we have to see the repulsion. We can predict the shape of the molecule based on the repulsion. If you have the lone pair in this position, that is the equatorial position, the lone pair is repelled by the bonding electron pair. So, this is a bonding electron pair. So, this is atom, this is atom. In between you have bond. That bond means electrons are there. That electron will be repelled by electron present in this region. So, that is a lone pair. So, there is a repulsion. So, angle between here and here is 90. Okay. So, this is a 90. Okay. Similarly, this lone pair is repelled by this bonding electron pair. So, because there is a fluorine, there is a fluorine. So, there is another 90 degrees. So, if you have a structure where the lone pair is occupying the equatorial position, then you will have 2 90-degree repulsions. Okay. Let us see how many number of 90-degree repulsions present in this structure. So, if you take, this is a square trigonal bipyramidal geometry, for this structure, this is you consider this is a lone pair. Now, this, if you put the lone pair here, the lone pair is repelled by the bonding electron pair of this one. There is a repulsion from this bonding electron, there is a repulsion from this one. So, it experiences, this lone pair experiences 3 90-degree repulsion. So, it has 3 90-degree repulsion. But this structure has 2 90-degree repulsion. Okay, 2 90-degree repulsions. So, you have to choose a structure okay, based on the repulsions. The structure with the less 90-degree, okay, less repulsion is the best or the favored structure. So, between these two, this structure is a favorable structure because it contains 2 90-degree repulsion compared to this structure where there are 3 90-degree repulsions. So, repulsion is more because there is a more repulsion between the lone pair and bonding electron pair. Here comparatively less bonding electron repulsion, okay, bonding electron pair and lone pair repulsions. Now, what is the shape of the SF4? So, you have 2 arrangements like this. Okay. the lone pair, this is a lone pair, and then you have arrangement like this. Okay. So, lone pair and then lone pair and then you have a fluoride. Okay. So, between these two structures, which structure is the correct shape of the molecule? What is the structure? The shape of the correct shape, correct structure of the molecule is this one, because it has a 290-degree repulsion. Here there are 390-degree repulsions. This is the correct structure. Correct. Then the shape should be the shape of the molecule should be based on the arrangement of the atom, not based on the arrangement of the lone pair. Then the shape of this molecule is called seesaw. Seesaw shape. Okay. So, you can see that what is the shape? Seesaw arrangement. So, that seesaw arrangement of the geometry is based on the arrangement of these fluorine atom, not based on this lone pair. Now, let us see another molecule. Okay. BrF3. Now, you have to find out the structure of the molecule. So, the bromine has valence electron 7 plus 3 into 7. Okay. So, you have 28 electrons in total, the valence electrons. So, arrange them. Okay. So, there are 6 bonding electrons. So, 6 minus 22. So, you can arrange them like that. So, 18s are gone. So, remaining is 4 electrons. The 4 electrons would be added to the central atom here and here. Now, this is a Lewis dot structure for BrF3. Now, what is the shape of the molecule? Now, the central atom contains 2 lone pairs. So, this is one lone pair, this is another lone pair. Okay. So, in total, so there are how many pairs of electrons? 1, 2, 3, 4, 5. Okay. 5 pairs of electrons, 5 pairs of electrons. That means 5 regions of electrons. The best way to arrange 5 regions of electron density is trigonal bipyramidal. Okay. Trigonal bipyramidal. So, if you arrange the bromine at the central and then arrange the 3 fluorine atom in this way, okay, and then this is a trigonal bipyramidal. So, this is a lone pair, this is a lone pair. Okay. So, because there are 5 regions of electron density. So, as soon as you get 5 regions, the best shape is the trigonal bipyramidal. So, you draw the approximate structure. Now, which is the best way of looking, what is the best structure for this? So, in this structure both lone pairs are on the equatorial plane. You can also have in this way. Lone pair, here is the lone pair. 2 lone pairs are occupying the axial positions. You can also have arrangement in this way. Okay. So, lone pair. Okay. So, in this structure 2 lone pairs are in the equatorial positions. In this structure lone pairs are in the axial positions of the trigonal bipyramidal. In this structure one lone pair is in the equatorial plane, another lone pair is in the axial positions. Now, you have to look at the repulsions experienced by bonding electron pairs or electron pairs. Now, if you look at this structure, okay, here the lone pair repulsion is the greatest one. Here you have, so the lone pair is repelled by this bonding electron pair by 2. So, there is 1 here, there is 1, 90 degree. So, it has 2 90-degree repulsions. But if you look at this one, okay, this lone pair is repelled by bonding electron pair. So, angle is 90. So, here is a 1, here is a 1. So, similarly here, okay, there are 3 for this lone pair. Similarly, for this lone pair there are 6. So, 6 90-degree repulsions. If you look at this one, okay, so this lone pair, okay, is repelled by this fluorine atom. So, 290 and then this lone pair is repelled by this lone pair. So, there are 390 . Okay, there are 390° for this one, there are 690° repulsions. So, which structure has less repulsions? This structure has the less number of 90° repulsions. Okay, so that is why this is the shape of the molecule. Now, the shape is a T shape, this is called a T shape. T shape, okay, it has a T shape. So, T shape is is given to this structure of the molecule based on the arrangement of the 3 fluorine atoms, not by the arrangement of the lone pairs. Okay. So, in addition, one can also explain the structure, actual structure of this BRF3 based on the lone pair repulsions. Lone pair, since lone pair wanted more volumes, okay, so the best place for that to is to occupy the equatorial plane, because in the equatorial plane the angle between the atom to electron density here to here is 120°. Okay, so it is far away from each other. If you put the lone pair on the actual position, the angle is 90°. So, the best way to put the lone pair is in the equatorial plane. That gives the structure of lower energy. So, that is why the shape of this BRF3 is a T shape. Okay, it is a T shape because it looks like a T. Okay, this is a T. So, this is one terminal, this is another terminal atom, this is another terminal atom, this is a middle atom. So, it is a T shape. Thank you.